In this slide, we will have an example to use the bisection method, and this example is our widely known parachutist example. And we already solved this for the actual equation you can see here, and we already plotted this function and identified, for example, the root is in between 12 and 16. So graphically we defined this, but we want to be specific to get the exact value of the root. For that, we can move on to bisection. So first, have a graphical method to identify maybe lower and upper bounds, and then move on to bisection, iteratively solve it between these, and then get the root value exactly. So for that, we will use a threshold of epsilon s, which is 0.5%. And until then, we will apply the bisection and calculate the approximation error. So the first step is to get the upper and lower bounds, and we already got them here. So from the graph, we see the sign is changing, or an intersection with x occurs if xl is 12 and xu is 16. And that's why we can simply calculate an error value using these. If you remember, we said that we can have an initial error by using these values. Let's use that. And if you remember, our error value approximation was xu minus xl divided by xu plus xl. We showed this in the previous slides, and we want to use this to calculate the error at the initial iteration. So we set xu as 16, xl as 12, and 16 plus 12 times 100, and this gives us 14.29%. So with this 12 and 16, we have an approximation error of 14.29 at the first iteration, without even doing any midpoint finding or halving the range, let's say. And because this is smaller than epsilon s, which is 0.5, then we will continue on calculating. What we do after this, we will simply find an XR value between the lower and upper bounds by summing them and dividing them into 2. So we will get the midpoint of this, and this is possible by this formulation. And from here, the result is 14. So with this new value, we want to understand if the lower bound region or upper bound region is on the sign change, or actually if they have a sign change or not. And for that, if you remember, we were doing a calculation of simply finding the function values and multiplying those to get a negative value actually. So we will find f12. For example, the lower bound is f12, and the value of this is 6.114 if you remember. And we will also calculate f14 simply using this formulation here. We already have all the values. f14 is because of this, and this is 1.611. With these, we want to see if fxl times fxr are smaller than 0 or not. And if we use them, actually, because these are both positive, for this case, f12 times f14 is equivalent to 9.850, which is greater than 0. Then it is not on the left side, because there is no sign change. No sign change. That means the sign is changing between 14 and 16. 14 and 16. That's why our new iteration, in the new iteration, so let's say this is XR1, and in our new iteration, and these are actually XU1, actually let's say 0, 0, 0, 0, and this is XR0 as well. And in our new iteration, XL1 will be our XR value, and this is the XU value, 14, and XU1 is 16. So because the sign change is here in between these. In that case, with these values, XU, we can again calculate an XR. We can also calculate first the error as well, but let's get the XR value, XR1, and it is again the summation of these divided by 2, 14 plus 16 divided by 2, which is equivalent to 15, and the epsilon A is again lower and upper bound differences for 16, 14 divided by 16, 14 times 100 is equivalent to 6.67%. You can see that we reduced the initial error, which is 14 over here, to 6.67 by choosing our prediction as 15 in the first iteration. If we continue on this, we can get other values as well. So in here we will again with 15 make the sign comparison. Then we will say fxl times fxr, which is actually now fxl is so xl is for 14 and xr is 15. For these we will use the function values for 14 and 15, which are 1.611 times for xr, it's minus 0.384. And you can see from here we have a sign change. It's because it's minus. The value is not important actually. The sign is important here. So if there is a sign change, that means now if we also look at the graph, if this is, let's say, 15 and this is 14, in between these there is a sign change, and that's why the root is in between these. That's why now in the second iteration, let's write in the second iteration, the lower bound will be the same. In the first one, let's go back to first. Upper bound stayed the same because there was no sign change when we multiplied by XL. But when we multiply by XL function value and there's a sign change, then the lower bound will stay the same. Then XL2 is the same, 14, but XU in the second iteration is the new XR value, which is 15 now. With these we will calculate a new XR2, and it is 14 plus 15 divided by 2, 21 divided by 2 basically, and it becomes 14.5. And with this we can again calculate the EA, and for EA actually we don't need the XR value but the XL and XU values, 15. So with the second iteration that we mentioned in the previous slide, it is the third iteration here for the 14 and 15. Basically we obtained the error reduced to 3.448. Remember that the previous error was this and now this. So we plotted, actually we showed all of the iterations up to iteration 6 over here. XL and XU is from 12 to 16. So XR was 14 here, you can see. Actually The initial error also we can calculate, we said in the previous slide as well, and it was calculated as 14.29. We can just simply write it here. It's 14.29 at the beginning, with the division of the difference and summation of these, we obtain this. And you can also see that we also calculate an epsilon true error by using the true value. Actually, we don't know that, but the question actually gave it to us. The solution of the book gave it to us. But assume that we don't know, so we don't need the true calculation actually. But if we know the true value, then we can make a calculation and make comparisons. The true value is mentioned as the true C is 14.8011. Let's keep it in mind. And for each XR value, by simply subtracting from here and dividing to this and multiplying by 100, we calculate these values. Now let's investigate the iterations. Initially, we had the middle point as 14, and because the function value is changing the sign between 14 and 16, we kept the upper bound as 16 and kept the lower bound as the XR value 14. Now in here it's 15, as you can see, and we see that the sign is changing between 15 and 14. That's why we kept the lower bound the same, but changed the upper bound to the XR value. And here we calculate the XR as 14.5. And with the 14.5 and lower value, we see that the sign is changing between the upper and this. So the lower is this value and upper kept constant as the previous one. And then the result is 0.75. We can continue because we want from the example a 0.5 error calculation. Actually, for the true value, we already reduced lower than 0.5, but for the approximate also, we want to go down to 0.5%. Here it's 1.7 now. And for 14.75, the sign change is happening with the upper bound, in the region of upper bound. So we kept the upper bound the same, but changed this value. It's 14.75 for the lower value now. And the midpoint of this is this value. And for that, the error is still higher than 0.5. So we continue. For iteration 6, now we see that XR and lower bound between these, there is a sign change. So this becomes the same. XL becomes the same, that's why. And XU, the upper bound, becomes this value. And the midpoint of these is this. And the error now is lower than 0.5%. So we can stop here. But if you want, you can easily continue. And you can see that this is very, very close to the true C value. And the true error shows that. It's very low, it's even lower than 0.1%. So here you can see the first three iterations. First between 12 and 16, the midpoint is 14, like here. Then over there, we actually see that these sign changes at the upper bound, so we keep the upper bound. Then 14 and 16, the midpoint is here, the sign changes on the lower bound, so we keep the lower bound. Then if we continue 14 and 15, the sign change now is with the middle and upper bound, so we keep the upper bound. So it goes this way, we can say. And we made a comparison of the approximated errors and true errors on the right hand side. You can see the approximate error going like being halved at each iteration almost. So it's a linear reduction of the approximate error. For the true error, there is an oscillation a little bit. So you can see it's reducing, then increasing, then reducing and increasing, etc. So this oscillated behavior is because of the actually the root being on the left or right hand side of the middle point. So the true root can lie anywhere within the bracketing interval, and if the true and approximate errors are far apart, the interval happens to be centered on the true root, and that's why they are closed when the true root falls at either end of the interval. And another feature or behavior we see from this is that the approximate error can predict the general behavior of the true error, and it's always larger than the true error. And this is, we mentioned earlier that the approximate is always larger than the true error, and this example shows a good demonstration of it. And eventually we see that there's a reduction, and we will capture the final solution easily. And accurately, we can say we can increase the iterations further if we want to, but 0.5 was our initial target, so we stopped at the 6th iteration. So for this example, we can also use the determination of number of iterations equation. If you remember, first of all, we said earlier that we can use the initial lower and upper bounds to have some idea about the number of iterations, also the error value. What I mean is that, so let's say our initial value is delta, so let's don't say initial value, but the delta x0, which is the initial difference between the upper and lower values. It's 16 minus 12, because our initial determined values were these, and this was equals 4 for this example. And if you remember, we said that the error at nth iteration can be determined as delta x initial divided by 2 to the power n. We gave this formulation before. Here, if we write, so we know from the previous slide that after 6th iteration, the error was below 0.5. So for n equals n equals 6, EA 6 is equivalent to 4 divided by 2 to the power 6. And the EA value from here is 0.0625. If we multiply this by actually this is the value, we don't need to multiply with anything. You can see that we obtain a 0.06 absolute value after the 6th iteration. So this is the absolute value, absolute error, let's say. So what we mean is that from the beginning, if we decide an n value, we can easily find an error, and if this is small enough, we can say that okay, n equals 6 is good for the iteration number as the iteration number. In another case, we can use finding the n value if we know the error value. For this case, for example, let's say initially we know, or assume initially we target EAD. It is called EAD 0.0625. Then we can simply use this formulation, n equals logarithm delta x0 divided by EAD divided by logarithm 2. Sorry, not like this, but the 2 is just logarithm 2, like this, is equivalent simply logarithm 2 delta x0 EAD. So here delta x0 is 4 divided by EAD is 0.0625. If we take this logarithm, the iteration number is 6, and this shows that if we know if we decide an EAD which is 0.0625, then we need to use just 6 iterations. We can make this initial assumption and we can do the calculations for 6 iterations only. If that means if this is acceptable beforehand, we have this information, or we just set this as a threshold, then we can use 6 iterations and get the results easily. So these formulations are handy and useful to decide the number of iterations or the error, absolute error value from the beginning for the bisection method.